filter out unsound candidate triples, that's the contracts, has been a thorn in the side of any biabduction practitioner since time immemorial. This 15 years ago. And we absolutely agree, it's not great, and we therefore set out to make our tool Broom sound in a single phase, and we actually achieved this without changing the logic, the biabduction procedure, or the abstraction procedure whatsoever. And therefore, our techniques are actually completely generic and can also potentially be used in other analyses or other analyzers as well. But before I get into what our techniques actually are, let me give you a quick introduction what the problems, the unsoundness problems actually are that we need to solve. The first one can occur if we have simple branching. In this function choice, we take two pointers and non-deterministically read from one of them and return the value. Now the question mark here is essentially a non-determinism operator, which can stand for something like file input, network input, user input, you name it, right? Something that cannot be described in terms of the actual parameters of the function. And we as humans see, well, this function is only memory safe if at the function axis both pointers are allocated, aligned, not null, you name it. Now let's have a look at what the analysis will do. In the beginning, it will start with a precondition just saying top. So we don't have anything yet which we need to compute, or which we need to be memory safe until this point. Then we do a step in one of the branches, and therefore we need to load from, in this case, for example, P. So we need to have P to be an allocated pointer, it needs to be aligned and so on. So we just say we need the points to predicate for P in the precondition. And similarly, for the other branch, we get the same thing with Q. Now the analysis will say, okay, I found two potential preconditions, one with P, one with Q. Let's have a second phase and check whether these are sound. And unfortunately, as we already noticed, they are both not sound. So in the end, the analysis will not find any precondition or any contract for this very simple function, which is not great, right? And this is something that has already been described back 15 years ago in the first paper about biabduction. There, the authors didn't really find a good solution other than the second phase, but they at least figured out that a heuristic combination of candidate preconditions might cover some of the branches. But that's not enough to get rid of the second phase, right? More recently, the tri-abduction idea that was developed for the outcome separation logic was introduced as a bit more of a foundational idea to actually solve this problem. Essentially, now we don't have two sides of the biabduction operator, but now three sides, and we try to compute a single precondition for both branches at the same time, which is perfectly fine, would solve the problem, but is unfortunately a bit unfeasible in our specific use case, since it would mean to implement completely new reasoning mechanism on top of our existing biabduction. And so we took a step back and looked at the problem from a different angle. Because biabduction as a reasoning technique is sound. We find the correct preconditions. We just don't share them with all the other points that are equally reachable from the same precondition. So what we therefore developed is our new technique called shared abduction. And the main idea here is that compared to before, where we only have a precondition formula and a current state formula, we now have a single shared precondition formula with potentially multiple current state formulas at different program locations. And it works like this. If we then do a step in an analysis, we'll once again find out that we need the points to for P. We will therefore add it to the precondition. But at the same time, since both the branches are equally reachable, we also add it to the other part of the other branch. And similarly, if we find out that we also need Q to be allocated, we also add it to both the precondition and the other current state formula. And therefore, together we get the correct and expected precondition of both pointers and the expected postcondition of a disjunction of the two results. And this is a very easy but very powerful idea that works also for arbitrarily nesting of branching, for deterministic and non-deterministic branching interleaved, you name it. So have we solved all problems? Unfortunately not yet. There's another problem with unsoundness, and that comes, as we've heard before a little bit, if we have loops and want to do abstraction. Now if we look at this very simple function here, traverse even, it traverses a linked list with two nodes at a time. Okay, this is not very realistic, but it's a very simple example that we should be able to handle, right? Okay, let's have a look. What does the analysis do? We start again with top. We'll find in one step, after entering the loop, that we need one node of the list. And then another step, another node. Okay, now we're back at the loop head, obviously. Now we don't want to find infinitely many nodes. We want to do some widening, some acceleration, some abstraction. In this case, for example, we could see, okay, 2 list nodes together make something like a list. So let's exchange it for the abstract list segment predicate, going from X to some L2. Now, unfortunately, this list segment specifically does not encode the length of the list. But as we've seen, the function actually traverses 2 nodes at a time, so it's only memory safe for lists of even length. So this immediately is unsafe as a precondition. Now, unfortunately, the analysis will not ever figure this out, or at least not yet. It will try to find out, is this now a fixed point of the analysis? So it does another loop iteration, and then it does a second phase and only finds out then that actually this does not work. So what is the problem here? Is it that we should be able to encode even length lists? Is it that the abstraction should be better? Not necessarily, I'd say. Actually, we can find similar examples for pretty much any kind of logic and any kind of abstraction operator. So that's not really necessarily the solution to the problem. That we actually, it can be a solution to this specific example, but not in general. So what we actually want to have to get rid of the second phase is a way to figure out immediately that we have reached a sound fixed point, essentially a loop invariant, instead of just a fixed point of the analysis. So our idea is now to use biabductive loop acceleration with 4 steps. The first one, just compute or just analyze the loop once. The second one, use a heuristic to compute a candidate invariant. The third step, try to reductively verify this invariant. If it fails, we fail early. If it succeeds, we can, in the fourth step now, actually construct a loop fixed point, or a fixed point of the analysis for this loop, which is guaranteed to be sound. That's the basic idea. Let's have a look at what this means for this specific example that we just seen. Once again, we have the 2 list nodes, which we get from the analysis. Now, as we've said, list nodes kinda abstract 2 lists. And specifically, if we want to figure out a loop invariant, we kinda need to figure out that we are at some point while traversing the list. So let's say we have a list segment from the original value of X to some location L, where X is currently at L. And we might have some remaining list up to null because we ignore cyclic lists for now. And with this idea, we can then construct our invariant, or candidate invariant, by just saying, okay, in the precondition, we have the 2 parts, which is something that we need as a precondition. In the current state, we've already traversed from the uppercase X to L, that is the blue part. It might contain some changes, something like deallocation or so on. In this case, it doesn't. And we still need to go from L to null. And that's essentially the idea for the invariant. Now, deductive verification will just enter the loop once again. It will assume that L is not null, which was the loop condition. And therefore, we immediately know that the list segment from L to null cannot be empty. And so we immediately can get a single new node out of it, which we call L prime. But unfortunately, now we can't get a second node out of it, which would allow us to actually verify 2-step example, which obviously we can't. And therefore, we can immediately fail fast. Now, if, however, would assume that the function actually only does 1 step at a time, this would already be sufficient to show that we have reached, or that we were able to get through the loop. We can now do abstraction once again, fold the list, the extra node into one of the list segments, and essentially get back the invariant, and have shown that the invariant actually is an invariant. And with this, we can then actually also succeed fast by just constructing the fixed point of the analysis as given a list from X to null, it will return a list, same list from X to null, and the program variable X is now at null. And that's essentially the whole idea, well, to just make sure that whatever we get out of the loop for the analysis is actually sound. We will not always succeed. The heuristic in this case will probably be very similar to what we used before for the abstraction. But we are a bit smarter because we now directly check whether it actually is sound. And as you've seen, we not only fail fast, but you also succeed quite fast. And this actually improves the runtime of our tool Broom quite significantly. So we have implemented our techniques as proof of concept techniques, which we call now the brush analyzer. compared to the Broom analyzer, which is the old one. So the x-axis is our new tool, or the tool with the new techniques. The y-axis is the old version. And as you can see, most of our experiments, which are sometimes handcrafted, sometimes from our own small benchmark, are above the equal timeline. To be more precise, overall, we almost reduced the runtime by 50%. For loops, or programs with loops, we actually reduced the runtime by 95%. Primarily because we reduced the amount of analyzed loop iterations by 66%. That's just the second phase and the speed up in the first phase. As you can see also, the branching part is not that much faster, primarily because the branching examples in this benchmark set are all deterministic, since Broom cannot handle non-deterministic branching, so that's just a cherry on top. And yeah, that's essentially what we get out by just adjusting the symbolic execution of our analysis, and not the logic, not the biabduction procedure, not the abstraction procedure. And as you might have noticed in the beginning, the title was Extended Abstract, since this paper, or like the work for this paper, or the work that I just described, will be published as a paper at ESOP later this year. So if you want to have a look at the full version, please go ahead. That's it from my side. Thank you for your attention.
Thank you, Florian. Any questions? No. I have a question. In your new biabduction technique, is it as complete as the original one? Because suddenly you can only biabduce specs of a certain form because you coalesce those pointers.
So we have not changed anything about biabduction itself. So the reasoning technique is really the same thing. And for the branching example, any program without branching and loops will be completely the same. With branching, we can now additionally handle non-deterministic branching. And for loops, our heuristic is essentially the same as before, so we can handle at least the same amount of programs. Just some that might time out can be now handled because we're now faster. So we are just strictly better. We can handle the same things as before and some more.
Cool. Well, thank you.